Hello, and welcome back to this series of video tutorials where we learn how to use Lean to create simple maths proofs. So this is the third in this series, and today we're going to do a little bit of revision because we've learned quite a lot actually in the first two videos, and it's worth kind of just practicing it a little bit and letting it sort of settle in with yet another very easy task. There is something new, I guess, in today's video, and that is today's proof will be entirely symbolic. It won't involve numbers, and that's just to kind of really showcase that the kinds of proofs that Lean can do can be general and not just about proving one number is bigger than another or that something equals 5, which is what we've done before. So if there's anything new, it's that. It might seem a small point, it could be a big point actually, but being able to prove something in general is quite powerful. So we'll practice what we've learned, and we're going to choose a proof task which is still simple but is actually symbolic. It doesn't involve any numbers at all. So let's have a look at it. So the task we've set ourselves is fairly simple. We're given a z equals y squared, and we're also given that y equals x plus c, and we're told that all of these things, x, y, z, c, are all real numbers. We're not given what they are, so it's general in that sense, and what we want to prove, given these two facts, is that z is x plus c all squared. Now again, you might say, this is really easy, is it worth even bothering? But just to remind us, the reason we're doing these very simple tasks is to focus on what the Lean code looks like, the Lean proofs look like, without getting distracted by advanced mathematics or kind of puzzles and tricks in mathematics. So this isn't a course on maths, it's about how to use Lean to write simple maths proofs. So we don't want two distractions, we just want the one, which is Lean. So let's just think a little bit more about what we mean by general. So z can't actually be anything. What are the really free variables, as it were? Because z depends on y, we've seen that here, and y depends on x and c, but x and c don't depend on anything. So it's general in the sense that x and c could be anything in the set of real numbers, but once we imagine them or pick them, then y is set and z is set if they're constrained. But it's a general statement because as long as x and c can be anything, and then whatever they are, z is x plus c all squared. Right, so as you know, we've kind of been following this kind of working pattern of trying to write a kind of a proof in a structured way. And as we've said before, it's actually quite difficult for easy tasks like this because our brains want to jump ahead to the conclusion, and our brains don't really want to think about the kind of line-by-line justification. But we need to train ourselves to do that because that's how we use Lean, that's how we write Lean code. We do it step by step and justify each line. So it's good practice to kind of do that even with these almost trivially simple tasks. So here's a maths proof that we've written out. So we've written a good habit to write out the given facts or the hypotheses, things that we are given to be true, things that we can assume. And we're given two facts. Z is y squared, and that's a given fact. We've labelled it 1. And y is x plus c, and that's a given fact, and we've labelled it 2. Then into the main body of the proof, we start with z. And what is z? It's y squared. Why is that? Because of fact 1. Now that might sound like, being really pedantic, but again, it's the kind of thinking we want to get into because it'll help us write Lean proofs. So that's good. Z is y squared. Now we've established that and we've justified it using fact 1, so we can't argue with that. How do we make progress? Well, we look at what we wanted to prove, which is this thing here, z in terms of x and c. Is there anything that will help us? Actually, yes. The second fact will express y in terms of x and c. So that's kind of probably a good direction to go in. So why don't we use the second fact to rewrite y in terms of x and c? So we substitute y with x plus c. And as it happens, that takes us straight to the conclusion. So not difficult at all, but this kind of structure is what we want to be able to do again and again. And again, notice there were no numbers here. This proof is not about comparing one number is bigger than another, or a variable is 5 or anything like that. It's purely it's abstract in that sense. So again, if you wanted to kind of slow down and think through that proof, you can download the slides and read the explanation if you wanted to. I won't bore you because I've just spoken about it, but you can do that if you want to. Or there's a blog as well where I write up what we're trying to do in words that make sense. And when I'm speaking to you like this, I kind of speak from the top of my head, which sometimes isn't always the best choice of words. So the blog is there as well. So let's look at the lean code that implements that proof. Now hopefully this should be more familiar now, because the first two videos that we did all had code of a very similar structure, almost identical, and we talked through, in the first one we just kind of looked at some of the highlights of the code, we just made some observations. In the second video we did talk through line by line, instruction by instruction, what each part of the code did. So if you kind of need a refresher, do go back to the second video, but we'll refresh ourselves here briefly. So that's the comment. This is importing the maths library into Lean. Lean is a programming language. The maths library has all the magic that we want to use. This tactic is the tactics that we want to be able to use to justify moving from one line of the proof to the next. So when we kind of progress the argument in the proof, we have to justify each step, and it's usually done with tactics. And again, the last two videos introduced a few of them. The structure of the proof is pretty much the same. It is exactly the same as the ones we looked at before. So you may have a name for the theorem that you're trying to prove, but because we're not going to use it again, we use a special name, example, which means it's kind of like an anonymous one. We set out what the variable types are. So these are real numbers. We set out the hypotheses, the two facts that we're given. So hypothesis 1, we've named it h1, that z is y squared. Hypothesis 2, which we've named h2, y equals x plus c. Those are two given facts. And then we write the objective, the proof objective, the thing we're trying to prove, which here is z equals x plus c all squared. And then after that, this symbol means what follows next is a justification of a proof of what preceded it. So that means everything after that is the body of the proof. Again, a reminder that calc is a strategy. It's a simple, direct proof by calculation. We said we weren't going to talk a lot about that because for now it doesn't really matter. It'll make more sense when we can compare it to alternative kinds of proof. So for now, we can almost make it invisible. So we start our first line of the proof with the thing we want to prove something about, which is z. So we start off with z, and z equals, well, what does z equal? Well, just like our maths proof, which we can go back to, we said z equals y squared using fact 1, and that's pretty much what we've done here. Z equals y squared, y, by the rewrite tactic using the first hypothesis. So her first hypothesis said z is y squared, so we can rewrite z in terms of y, it kind of matches the pattern. So whenever we see a z, we can use y squared. So z is y squared, and we've justified that using this hypothesis and the rewrite tactic. And it's better that the language isn't overly kind of crowded with special cases. So, the best languages are small, with smallest syntax. I'm not saying Lean is small, but that's kind of why I'm kind of content with that. Then the interesting bit, which is this previous expression then equals something else. It equals x plus c all squared. And how do we justify that? Well, we justify it by the rewrite tactic again, and this time using hypothesis 2. So just like the maths proof, we are substituting y with x plus c because we can use the second fact. That's exactly what we've done here. We've replaced y, we've rewritten it with x plus c, and we have to explain why that's valid. So we say by rewrite rule using the second hypothesis. And that actually is the conclusion. So this matches what we set out. We wanted to say z equals, so z equals, and this expression here, x plus c all squared. So once we've got there, the proof is done. And just a reminder that this underscore means the previous expression, which means that one there. You could write y squared equals, but we can, it's like in normal maths, I think we've written it here as well. Here to the left we don't write anything, and you can see in longer proofs the left hand side is often left blank because it means the previous expression. So that actually nothing particularly new there, but what is interesting was that there's no numbers involved. This is purely symbolic. So good practice this exercise, and to see that Lean can be used to prove more general results which don't depend on knowing what the value of a variable is. So the thing to take away from there is that code is almost exactly like the code we used in the previous video. It's actually one line shorter because in the last one we actually had to do a numerical calculation, and we don't here. Yeah, so not too difficult, hopefully. That I think was just practice really, and that's sometimes good to do. If there's any kind of questions or concerns, do kind of get in touch with the chat and on the YouTube comments, and we'll kind of explore any confusion. Yeah, again, I'm not going to read all this. You can download the slides and have a look at the content yourself, or look at the blog, which writes more in long form. And I finish usually with, well, every time I hope, with an easy exercise. And just a reminder, the exercises, I call them easy because they really are not about a mathematical challenge or a mathematical trick or a puzzle. They really are designed to have the maths easy, so the focus is on practicing and using the Lean concepts that we've just learned. So this one is almost trivially easy, and hopefully you can do it. And if you can, it means that you've learned what you meant to learn. So in this one, the idea is to prove that z is x, given z is y and y is x. And you say, wow, that's almost trivially easy. Let's draw a picture. Z equals x, and we are given z equals y and y equals x. So z equals y and y equals x. So that's trivial, isn't it? You couldn't get easier than that. But the idea is to practice doing that in Lean code. So you can imagine these are the two hypotheses, maybe you call them H1 and H2. And then you might write, well, let's talk through the strategy again. So you start with the thing you want to prove something about, which is z equals, and what does it equal? Well, the first hypothesis tells us that it equals y, so we'd probably justify it with the first hypothesis. I won't write the code because that's your task. And then we say, okay, that's great, we've expressed z in terms of y. Now we need to, we're aiming for x here, so is there a way we can express y in terms of x? And that might use the second hypothesis. I've almost given you the solution, haven't I? I haven't given you the justifications, so if you do it, that's good practice. So not too difficult, but good practice. Any problems with that one? Again, get in touch with the comments, and we'll have a discussion there. Fantastic. That was a short one, so I hope you kind of found that useful as practice. Next time we're introducing something new. Next time we'll get Lean to do some algebra for us. So we're just stepping up a little bit. So that'll be something exciting to look forward to. See you then. Bye.